Section 2.3, which is going to be the last section we cover in Chapter 2 for sake of time, is all about rules of replacement. So our last section was on the rules of inference, right? This allowed us to infer what was true. Rules of replacement allow us to replace certain things. So let's take a look. So the first step was De Morgan's laws, which we've proved, right? We proved De Morgan's laws. Next, we've got commutation, which tells us we can reverse the order of conjunctions and disjunctions. P, Q, or P is the same as P or Q, okay? We can also rearrange parentheses and conjunctions and disjunctions. I gotta get away from this red pen. There we go. Distribution is another rule where we can, just as multiplication distributes over addition, in logic, a conjunction can distribute over a disjunction and vice versa. Double negation, two negatives make a positive. You know, normally two wrongs don't make a right, but in math it kind of works. Transposition, it's also called the contrapositive. I'll show you what that is on the next slide. Exportation and tautology. Tautology is everything's true all the time. So let's take a look at what these rules of replacement look like. So I have De Morgan's laws, which we've seen before. Commutation says if I can flip the order. Association says, much like multiplication, if I've got all ands or all ors or all ands, I can switch where the parentheses are. Distribution is P and P or Q. I can distribute that. Same thing with P or Q and R. Double negation. Transposition, this one's kind of cool. It says if P implies Q, that's logically equivalent, so we can replace it, right? It's logically equivalent. To not Q implies not P. Interesting. We also have material implications. So P implies Q, not P or Q. We actually proved this in the first section 2.1 that this was a valid argument. I snuck it in there. I'm so sneaky. Material equivalence says if I have P logically equivalent to Q, then P implies Q and Q implies P. Like, that makes sense. If I have P is logically equivalent to Q, then P and Q or not P and not Q. One of them has to be true. And then exportation, if I have P and Q implies R, then P implies Q implies R. And then we've got tautology, which is P is the same as P and P. P is the same as P or P, right? That makes sense. So let's go ahead and justify the steps of this logic proof, okay? So we're going to use our old laws of inference and our new laws, okay? So if I have, and those new laws are on page, where are they? Page 74. So I definitely open up to page 74 so you can take a look at your laws. So the first thing I have is I know I got to get C all by itself. That's my goal. As you can see, we got C all by itself. So somehow I'm going to have to find P implies not Q in order to get C all by itself using modus ponens. So that's our first step. That's our kind of where we can see where we're going. If I have not or, not R, or P, right, I can distribute that negation in there using De Morgan's laws, and that becomes not P and not R. That's how we got from 2 to 3. So that's row 2, and that's using De Morgan's laws. You don't have to tell me just which one, because I know there are 2. Just write De Morgan's laws. Then I have not P and not R. Well, if I look at step 3, all I did was swap their places, and that's one of our new rules of commutation. So I used commutation on row 3. Next, now I went from not P and not R to just not P. Well, that is simplification. Next, I somehow go from not P and to not P or not Q. That's an example of addition, right? I can add whatever I want. I can even add a negation. Now we use rule, where is it? 16 for implication, right? Implication says that P implies Q is logically equivalent to not P or Q. Well, I have not Q, but I do have not P, so that gives me P implies not Q. We just leave our second part the same, and that's okay. This is material implication. This is one of those rules I always forget about, so I always want to double check it. So now I'm good. I've got P implies not Q, and I can use row 1 and row 7 using modus ponens to get C all by itself. So why don't we go ahead and write the formal logic proof for this statement. I have K implies L. Therefore, K implies L or M. Now that seems really kind of trippy, right? Because I've got lots of extra. I got an extra M from somewhere. I don't know where it came from, but we're going to prove it. So let's let this be row 1 is K implies L, and we're trying to prove K implies L or M. Now, this is different because all I have is K implies L. So I need to look at some rules of replacement to see how I can rewrite K or L. And I'm going to use material implication. So if I have P implies Q, that's the same as not P or Q, so not K or L. So that was material implication. On row 1. Next, I have, I can add an M, because I've got to get an M from somewhere. So I have not K or L or M. We're getting a little bit closer, so we've got to add. Now I can use association to redistribute. So I've got 4 not K or L or M. That was association. And then I can use material implication again to have not K to get K implies L or M. And there we proved all of our steps.